Hey guys, welcome back to Genius Learning. So in this problem I want to show how to deal with Ampere's law. So we're looking for a magnetic field, and in this particular problem we have an infinitely long cylinder, so just extends all the way up and down, and we have frozen in magnetization inside of this cylinder. So it's denoted by this arrow in the M. The M equals C S squared in the Z direction, so that's upward. All right, and that's for S less than R. So R is the radius. The big R we're going to use as the radius of the edge of the cylinder. So since the edge of the cylinder doesn't change in size, then we're going to say that big R represents that distance, and little s is anywhere inside of big R. And so here I wrote the cyclic cycle for R, phi, and Z, which is cylindrical. We're going to be using S instead of R. So it's the same thing. Little r is somewhere inside of here, less than big R. I'm just going to use S. Okay, so it's 0 outside. So S outside of R, so somewhere out here, we don't have any magnetization. So everything that we're interested in is inside the cylinder. Okay, and so this picture here shows J, right, which is our bound volume current in this direction, and we show our bound surface current in the opposite direction. Okay, and for both of them. So these were not given. We're going to find these two pictures right here in these two sections, and then finally we're going to calculate magnetic field over here using an Amperian loop. Okay, so we're going to leave this for last, and we're going to focus on how we found these two representations here. Okay, so first I want to look here. It says find the magnetic field inside and outside of the cylinder. Okay, so first let's look at the bound volume current density. Okay, and the formula for that, we have J bound is equal to del cross magnetization. All right, and so in your E&M books you should have these formulas. You can also derive them using the cyclic process, which I might do in another video, but it's not important. You'll be given these formulas. And so del cross M, right, is going to equal, you have your S hat, which is everything in here, right? You have your partial of the magnetization in the Z with respect to phi, minus the partial of magnetization in the phi with respect to Z, and all of them are similar but a little bit different. So here you have your phi, so everything in here, and you see I denoted S, Z, and then here you have a 1 over S, just like in the beginning, on the outside. And a tricky part that I put in blue, sometimes that people miss, you have the partial with respect to S, and inside you have S, magnetization of in the phi direction, and then normal over here, and the Z hat. Okay, so this formula should be given to you, or you can look it up in any E&M book. So let's find the bound volume current first. Okay, so what we have here is our magnetization, and it's in the Z hat. Okay, so the only thing that applies to us, it looks like it's going to be this right here, right? So this one right here is the only thing that applies to us, because magnetization in the Z, we have that, and with respect to S, perfect, we have that. We don't have Z and phi. We don't have anything in here that has a phi in it, so we can't use that. We don't have anything in here that has a Z in it, and it's not in the phi hat direction, so we can't use any of these. Partial of MS, we have S, but we don't have Z inside of this equation. Here we can use this because we're in the Z direction and we have an S inside. Okay, here we don't have any phi direction. Again, we're in the Z. And then here we have the S direction, which we don't have, and no phi in the inside. Okay, so basically everything is 0 except for this term right here. All right, so let's write that term. So we're gonna say now that our J bound is gonna equal del cross magnetization, which left us with a negative partial of mz, right, partial of s, okay, and that's in the phi hat direction. Okay, so this is the only thing that we're left with. Okay, perfect. So now, since we have our magnetization in the z hat, right, and that's equal to s cs squared z hat, we're going to put this in there and then take the partial of it. So we have J bound is equal to, right, negative partial of s, right? I'm going to take this partial and partial of s outside, and I'm just left with m in the z. So I'm going to replace it with that. So we got c s squared in the z hat, right? So I'm not going to write the z hat, and we have phi hat. Okay, so the z hat is denoted in here, and so we don't need to write it. We pick up the phi hat, which is what our formula gave us. Okay, so these are going to be the vectors that we stay with always. All right, so now we see that if we take the partial of this with respect to s, we're going to get J is equal to negative, right? The 2 comes down, so we're going to have a 2 cs, and the phi hat stays, and that's it. Okay, so having that, right, we could see that we're in the negative phi hat direction, and so phi hat usually goes from x to y all the way around and back, and it starts at 0, it goes all the way around to 2 pi. And so if it's negative, it doesn't start this way, right? We want to go the opposite way, and so that's why our J bound, right, goes in this direction here. So this is how we found our J bound current. So our bound volume current density is going to be on the negative phi, and so now we know why we got this as our direction for the volume current density. Okay, so now let's move on to here. Our second thing we have to deal with is going to be our bound surface current density. All right, and so this is the formula. Again, you could find this in your E&M book. You can memorize it. This one's shorter, but usually you'll be given this for an exam. So the surface current density is equal to the magnetization crossed with the normal. Okay, so let me show you where the normal is at. All right, and so I'm going to show it. Let's see. I'm going to show it up here. And so we're going to say that normal to the cylinder, right, is going to be outward. And so that's normal to this surface right here. See, it's perpendicular. And n hat is going to equal s hat. Okay, so this is a 90 degrees, and that's our normal to the surface of the cylinder, and that's going to equal s hat. Because remember, we're not using r hat, so s hat is the extension. All right, and so now let's see what this gives us. Okay, so at the surface, right, S is equal to R, because remember I said that R is the actual length of the cylinder. Anything inside of it is little s, and so at the surface right here, right, is going to be S equal to R, and so that's where we need to check for our bound surface current density. It only exists on the surface of the cylinder. Okay, so let's see, we got K bound is equal to the magnetization crossed with n hat, okay, at the surface. All right, and that's equal to, we're gonna have m, right, we're gonna put that in there, and so our m is c s squared z hat. Okay, and that's crossed with our normal to the surface, which we found over here to be s hat. So that's just s hat. Okay, and then we need to evaluate all of this at s equal to big R. Okay, so a review real quick. So the way we use this, the cyclic process, we're gonna have s hat, phi hat, and z hat. Okay, so to go this way, right, to go in this direction is gonna be positive, all right? And then to go in this direction is gonna be negative. So for example, if I do s hat crossed with phi hat, right, I'm gonna get a positive z hat. See that? So if I go s hat, phi hat, this positive, I'm gonna get a positive z. But let's say I go s hat crossed with z hat. So s hat crossed with z hat, right? Now I'm going in the negative direction. I'm gonna get a negative phi. Okay, and so maybe one more example. We can do z hat crossed with s hat. So z hat, now we're going this way, which is in this direction. So z hat crossed with s hat, it's going to equal a positive phi hat. So this is positive, so we're going s and then phi, positive phi. Okay, so these are just some examples. So now, how does that apply for what we're using? We have a z crossed with s, and so we have a z crossed with s. So we're gonna get, so let's see, z crossed with s hat, right? We're going in the positive direction. We're gonna get a positive phi. Okay, so this is what replaces these two cross terms. All right, and so let's rewrite it. We're gonna have k bound is equal to, we have c s squared phi hat, because phi now replaces z crossed with s, but we still have to evaluate s at the surface. And so k bound finally is going to be c r squared. We're going to change this s to r, and we're going to be in the phi hat direction. All right, so now we know that phi hat, right, normally goes from x to y all the way around. Okay, so 0 to 2 pi. And here it's telling us that phi is in the positive direction. And so we're gonna do this right here for k bound. Right, and so that's how we know that k is in this direction here. So we're going spinning in this direction here, right, in the positive phi hat direction. So that's how these two things were found. All right, the arrow we know because that was given to us. The frozen in magnetization is in the z. The j bound we found here to be in the negative phi hat, and the k bound we found here to be in the positive phi hat. Okay, so we're done with these. Now let's move on to magnetic field, all right, and Ampere's law. All right, so here we have our Amperian law formula, right? The closed integral of the magnetic field dotted with differential length is equal to mu naught I enclosed times I enclosed. All right, what does that mean? So let's draw an Amperian loop. All right, so let's think about this. We have current, so we have our cylinder, okay, and we have current flowing in the positive and negative direction, or clockwise, counterclockwise, right? And so we want an Amperian loop that is gonna allow us to measure how much current is passing through it. And so we need something that is perpendicular to that motion. So let me show you what I mean. If I draw an Amperian loop that looks like this, okay, so it's a square, and it's half inside the cylinder and half outside the cylinder. Okay, so if I do that, then you can see how we have our J, which is gonna go right through it, right? And then our K, which is also gonna go right through it, allowing us to measure the magnetic field inside and outside. All right, so you always wanna think about where you wanna put your Amperian loop. In other problems, if you have your J and K going up in this direction, then you wanna do an Amperian loop that is in a circumference here at the top, so that way the flux of the magnetic field will go through it. But that'll be for another problem. For this one, since we have it going in the positive and negative phi hat, we want an Amperian loop that's going to allow us to capture some of those magnetic field lines inside of the loop. Okay, so we drew our loop, all right, where this side here is inside. All right, and so now let's just outline this a little bit better. Okay, and this is gonna be our Amperian loop. All right, and then our Amperian loop should have a size to it. So from here to here, which is the entire length, we'll label that L. Okay, so let's draw the Amperian loop on this side. And I'm gonna show you why the S is now important. Notation. So this is the inside still. Okay, so this is the same Amperian loop. I just want to show something different. I don't want to clutter it all up here. So we still have this here as our length. Okay, and now what's different is that we're gonna have this length up to here, S. All right, so it'll allow us to measure. If it was closer in here, we're measuring a bigger surface area for our magnetic field lines to go through. If we're measuring closer to the surface, we're measuring less of them and closer to our surface current. Okay, so this is S, this big length here is R. Okay, so now here in this region here, okay, we're gonna say that B, right, our magnetic field is equal to 0, because there's no magnetic field lines going through this part of the Amperian loop, right? We're only frozen in magnetization. We only have field lines inside because the volume current is trapped inside and the surface current is trapped on the surface, right? So we don't have anything outside in this area. So B, or magnetic field, is equal to 0 outside. And so that's the first answer to one of the questions. So the magnetic field inside and outside. So outside, right, the magnetic field is 0. So it's 0 for S greater than R. And that's out here, this region in here of the Amperian loop. Okay, so now let's do the inside. So the inside, let's separate this a little bit here. So this was for the outside. And so for the inside, all right, we're gonna have S less than or equal to R, right? So now let's use our Amperian loop, and let's use Ampere's law for magnetic field, which is this. Okay, so on the left side, right, I'm gonna write my closed integral of B dotted with dl. Okay, so our differential length is gonna be Z here, because this is gonna be getting bigger or smaller depending, and that's what we're trying to measure here. So we're gonna have the integral of negative L squared to L squared. That represents the length of this. So you could have wrote 0 to L, right? Or you can write negative L over 2 to L over 2, which is the same thing. So these are our limits. We have B, and then B is in the Z direction. right? How do we know that? Because if we use the right hand rule, right, the current is flowing to the right, okay? And if we use the right hand rule and cup around, then our thumb points in the direction of the magnetic field, right? So current flowing, magnetic field in the thumb. And so we know that the magnetic field is in the Z, and it's dotted with the differential length, which is upward like this in the Z direction. So it's Z hat dz, right? Z dot Z is equal to 1. Okay, and then now let's work on the right side. We have mu naught, and for I enclosed, okay, we have a formula. So for I enclosed here, we have the double integral of J bound dotted with the n hat, which is normal to the Amperian loop. Okay, so I'll explain that in a minute. dA, okay, plus 1 integral K bound and DL perpendicular. Okay, so I'll explain those two right now. Okay, so for this side, we have B, which we can pull out, and all we have is the integral of dz with these limits. So we're gonna have BL on one side. Okay, now let's work on this side here. We still have mu naught, and now let's look at this here first. Okay, so we have two integrals. Okay, and J, we already know the value of that. Okay, so we calculated that over here. So we got -2 CS. So -2 CS in the phi hat direction. Okay, and this n hat is normal to the Amperian loop. So this is normal to the Amperian loop. Okay, so if our Amperian loop is here and we want the normal, it's going to be facing outward like that or inward facing you. You see, so it's a flat surface. And so normal to this surface here is going to be the phi hat, because the phi goes around, and so that is going to be that direction in the phi hat, right? Or this coming over this way is negative phi hat. So normal to this Amperian loop is going to be the phi, and so that's what we're going to write here. And so we got dotted with the phi hat, and now our differential area is going to be ds, because now we want to show that the I enclosed is going to be some differential length of s and some differential length of z. So this Amperian loop could be as big as it wants. So we're going to have ds dz. And so for those limits, now we're going to put, for the z, again, we're going to do negative L/2 and L/2. And for the s, right, let's write it in a different color here. For the s, we're going to go from s to r. Okay, so this is s right here, and this entire length is r. So here, right, is what we're measuring. S plus r. Okay, s to r. This is the region right here that we're interested in. So that's the region from s to r. All right, now for the last integral, okay, we have k. So we have one integral, and k we already know the value of, so let's write that in. We got CR squared phi hat. Okay, and now differential length perpendicular is going to be dz. Okay, so the differential length of k, again, k sweeps around like this, and so going upward like that is perpendicular to k. So k is going around, perpendicular to that motion is going to be upward which is going to be dz. Okay, so now let's see what we have. Okay, so let's take a look. Here we're gonna try to evaluate this integral, okay, in like 2 steps, since I'm running out of space here. We got BL, okay, we got mu naught, and inside here, right, let's separate these integrals first. So we can pull some things out. Let's pull out the -2c, and we're gonna have the integral from -L/2 to L/2 of dz, right? That's this and this integral. And then we have the integral of s to r, okay, and we have left over s ds. Okay, so that's for this side. And now let's work on this side over here. We have plus. We can pull out everything actually from this one. So we have, let's see, we have c r squared, and we have the integral from -L/2 to L/2 of dz. Okay, so now evaluating these integrals. Okay, I'm going to try to do it in 2 more steps. So these are just integrals. So if you get lost on this part here, just remember that you have this integral times this one plus this integral by itself. So let's see if we can squeeze that in here. Okay, mu naught. And so we're gonna have here, I'm gonna do this integral here is the only thing that's gonna be r squared minus s squared, because we have s. So that's, the s is gonna be squared over 2, and it's gonna cancel with this 2. Okay, so let's see. Well, I'm gonna leave the 2 there just in case. So we got 2c, all right? The integral from this is just gonna be L, right? Then we got, from inside here, we got r squared minus s squared over 2. Okay, that's from this integral. And then at the end, we have plus, let's see, we got c r squared, and from this integral, we're just gonna get an L. Okay, so now you should be able to see here that we're gonna have these 2's are gonna cancel, right? And so if I distribute this negative CL r squared, I have a positive CL r squared that are gonna cancel. And so the only thing I'm gonna be left with is CL s squared, okay? So I'm gonna have, and then I'm gonna move this L to the other side, right? I'm gonna divide by it, and it's gonna cancel with this one. So I'm gonna have, finally, B equaling mu naught, okay? And then I have CS squared. And of course we know that's in the z hat direction, and this is for s less than big R, which is inside. Okay, so this integral here, I mean, I can show you maybe over here. All right, this piece here I'll show you right here. Let's do mu naught. Okay, we're gonna have negative CL r squared, so negative CL r squared. That's for this first term here. And then we're gonna have a positive CL s squared, so positive CL s squared. So the 2's canceled, and this whole thing, we're left with this. And then this last term here, we got plus CR squared L. Okay, and so then we see that this term here cancels with this one, and we're only left with that term there, which we got here. Okay, oh, and the L, so this L here divides to the other side and then cancels with this one. So that's why we don't have an L here. Okay, so that's how we calculate the magnetic field inside and outside of a cylinder using Ampere's law. Okay, so this law here is very helpful. And it's similar to Gauss's law, but Gauss's law is for electric fields. Okay, so Amperian loops and Ampere's law is for magnetic field. All right, so if you guys found this video helpful, all right, please subscribe and comment below of any other examples you want to see similar to this. All right.